Well, all right, then let's continue. Well, that was linear independence, and we had this example of functions, and we checked that these are linearly independent. We can do this in different ways. Here in this example, we give different values for t, and we get a system of three equations with three unknowns. That means we can write this matrix, okay, and then try to solve it, and we get that here the only solution is C1, C2, C3 are all zero, and then this implies that the set is linearly independent. You could also what you could do is, instead of here row operations, you could check the determinant of this matrix. Okay, so the determinant of this matrix will be, oh, sorry. So the determinant of this matrix here will be non-zero. That means this matrix is invertible, and C1, C2, and C3 must be zero. You could also do that instead of elementary row operations. Okay. And another way to test the linear independence, well, we can write a Wronskian. Remember, the Wronskian is basically you have, let's say, f1 up to fn, n functions, and you write this matrix here, and this is called the Wronskian of the system of these functions, okay, the set of these functions. And we get that if the determinant here, the Wronskian, is basically the determinant of this matrix. If the Wronskian is not zero, then this C1, C2, Cn, they must be all zero. That means the system is linearly independent. Okay, so if the Wronskian is non-zero even at some point, then you have linearly independent functions. And when these functions are the solutions of nth order linear ODE, then we have this. Well, Wronskian is identically zero. Wronskian is zero at some point implies Wronskian is identically zero. So if the Wronskian, the determinant, is zero at some point, then it is zero everywhere. Okay, so this is not a trivial fact, but it is true. And we had this example where we checked that linear independence of these two functions and check the Wronskian, and we get that the Wronskian is non-zero. It's never zero, and conclude that these are linearly independent. Okay, and that was an exercise for you. Well, basically, what you get is, maybe let me write the answer here quickly. The Wronskian becomes e to the r1 t, e to the r2 t, e to the r3 t. It's basically, if you do that, you will get a similar thing like we have here. It's gonna be e to the r1 plus r2 plus r3 t times r1 minus r2 minus r1, r2 minus r1 times r3 minus r2 times r3 minus r1. And again, r1, r2, r3 are all different. That means the Wronskian is non-zero in this case as well. Okay. And these are some properties of the determinant. When you multiply a row by a constant, you multiply the determinant by that constant. And when you switch the order here, two rows, you get negative of the determinant. And when you take a row and add a multiple of this row to the other row, determinant doesn't change. So these are some rules of determinant. You may need it in future. Any question with this? Okay, now let's start our new lecture now. This is lecture 9. And here, this is 7.4 in the book, basic theory. Basic theory of systems of first order linear ODEs. Okay, so we will discuss the theory of this systems, and then we will solve some equations. Now consider a linear system of ODE, the homogeneous. Homogeneous means, remember, you have on the left-hand side an equation, on the right-hand side you have either a function or 0. If you have 0 on the right-hand side of the equation, we say it is an homogeneous equation. So first we will consider a homogeneous equation. Homogeneous systems of first order linear ODE. It's given by, remember it was given by some like that, x prime t minus a times x is a vector, okay? A is the matrix with some functions, entries, okay? So this is a matrix. Is equal to 0. Or we can write this, usually we write it like this. Instead of this, we write it x prime is equal to a times x, okay? So we understand from here, A is the matrix with some entries of functions, with functional entries. X is the vector. So X is here, vector function. It is x1 t, x2 t, and xn t, like this, okay? So this gives you n equations. Here, it's an n by n matrix. A is an n by n matrix, and we get n equations in this system. So we have this following theorem. This is called the principle of superposition. Well, it says basically if you have two solutions, two vector solutions, then their sum is also a solution, okay? Or they, even more than that, their linear combination is a solution as well. So suppose that x1 and x2, these are vector solutions, are two solutions. So they are vectors like this. Okay. Sometimes I don't put the vector notation, but from the content, you will understand that I mean here vectors. Okay, when we solve system, the solutions are always vectors with function entries. These are solutions of, let's call it here star. Okay, this star. Then any linear combination like this, C1 x1 plus C2 x2. C1 and C2 are real numbers, is also a solution where C1, C2 are constants. Okay. This is quite easy to show. You simply plug this combination into the system and you can get that it's a solution. Let's maybe do it. Proof.
Hocam bir şey sorabilir miyim?
Evet.
Farkları da bir solution olabiliyor mu?
Farkları da olur. Maybe we should say here with difference as well. Yes. Well, because why I didn't put minus sign here, because C2 can be -1, basically. Got it?
Yes.
Right?
Sorry, can I also ask one question?
Number as well. Yes.
What does this one in brackets mean? 1 and 2 in
It is the
like upper text.
first solution and second solution, basically. We just
okay.
It's a name.
Okay, thank you.
Number 1 solution, number 2 solution. Okay. All right. Let's show this. Well, basically, we check this equation, x prime is equal to ax. So C1 x1, I will not put vector notation to make it simplify. Okay. C2 x2, another solution, and take the derivative of this and check that whether this is equal to a times this. Okay. So what is this? This is basically C1 x1 derivative plus C2 x2 derivative. Okay, but x1 and x2 are the solutions of the system. So this is nothing but C1 a times x1 plus C2 a times x2, because they satisfy here this equation. Okay. Well, what is here? We can take a out here. Take a out. And what is the remaining part? A is common here. A is the matrix, remember? It is C1 x1 plus C2 x2. And this tells you basically C1 x1 plus C2 x2 is also a solution of star. Make sense? That's it. So we prove this result. So what is the purpose here? The purpose is to construct a set of solution which makes a basis for any other solution. So let me write this. Our purpose is construct a set of solutions to the system here. Maybe let me write this again. Ax, x prime is equal to ax, to the system x prime is equal to a times x, so that any other solution is a linear combination of them. Okay, so this set is called this. It's a basis. Okay, maybe let me write here. This set will be called a basis. We will call it basis. Okay. Now let's consider the initial value problem now. Consider the initial value problem. Again, we have a system of equations. X prime is equal to a times x. Okay, and let's put it here, vectors. And x, the vector at some point, we give the initial value. This is the standard vector, 1, 0, 0. Here we put 1 here, the ith entry here. This is the ith entry. Okay. Then existence uniqueness theorem says we did this for ODEs, but it is also true for system of ODEs. So existence uniqueness theorem says there is a unique solution to this system by existence. Maybe I should say here, A is a matrix, n by n matrix, with continuous functions. So each entry is a continuous function. Okay, this matrix will consist of some functions, and each function is a continuous function in an interval around this initial point. Then existence uniqueness theorem says there is a unique solution. Uniqueness theorem. This system, this IVP, the IVP above, has a unique solution. without the initial conditions, it may have many solutions, but with the initial condition, it becomes an initial value problem, and there is a unique solution. There's only one solution, okay? And let's call it xi, okay? So here I is, remember, it determines the initial value. You see here, ith entry is equal to 1, and with this initial value, we have this solution, okay? We call it x to the I. It's the name of the solution, basically. All right. Now we have the following theorem. Which says basically, well, when I is equal to 1, we have one solution. That means the initial condition is when here we have here 1 and 0 rest. When I is equal to 2, the second entry is 1 and all other are 0 and so on. And for each, we have a solution. Let's call it, so this set of vectors, vector functions, let's say. x1, x2, these are the solutions of the here IVP, xn, they are all vector functions like this, okay, is linearly independent. Okay. Well, there's one question: what happens with when the second entry is 1 here? So basically, if you have 0, 1, 0, 0, 0 as an initial condition, then for this you have solution x2. Okay, x2 is basically a set, a vector function. Okay, so we give a name for this. There is a solution x2. When we have 1, 0, 0, 0, with this initial condition, we have the solution x1. Okay, this vector. All right. So these are all solutions. For each, we have one solution. Okay, unique solution. X1 is a unique solution of unique IVP, because IVP will change when you change the initial condition. For each initial condition, you have one IVP and you have one solution. And we give a name for this. Well, if two entries are 1, okay, there's one question: what happens in this case? 1, 1, 0, and 0. Well, there is also a solution, but right now we are not interested in that, okay? There is also a unique solution because it gives an IVP as well, but we are not interested in that solution, okay? Right now. And actually, that solution will be the sum of these two. Think about it, okay? With 1, 1, 0, 0, 0, the solution is x1 plus x2, but that's not the point here, okay? Okay, there's one question: can we put the I here bottom? We don't prefer that. Why? Because I mean, you can do that. But it's gonna be confusing in future. The reason is let me explain. Okay, this notation we have to be careful because x1 when we write x1, it's a vector, and it consists of such functions like this: x1, 1 of t, okay, x1, 2, t, and x1, and maybe let's write it like this, okay, t. So you have n functions in this vector, okay? Each of them is like this. You can use your notation as well, but you have to be careful with the subscript as well, okay, in that case. All right, let's show this result. This set of vectors is linearly independent. The proof is simple. It follows from existence uniqueness theorem. So suppose that we will show that this set is linearly independent. So we will suppose first C1 x1 plus Cn xn, this combination is equal to 0, and we will show that C1, C2, and Cn, they are all 0. Well, at t is equal to t0, let's see what we get. We get from, let's call it double star, okay? From double star, we get C1 x1 t0 plus Cn xn t0 is equal to 0. But remember that here, what is this? x1 t0. x1 t0 is basically, it's the solution of this IVP with I is equal to 1. So x1 t0 will be 1, 0, 0, okay? And next x2 0 is x2 t0 is 0, 1, 0, 0, 0. And this one, for instance, 0, 0, 0, 1. Okay, so what you get from this is basically this 1, 0, 0, 0, 0, 1, 0, 0. And you continue like this, 1 here, all others 0, okay? Identity matrix times C1 Cn is equal to 0, 0. But identity times C1 Cn is nothing but, this is nothing but C1 up to Cn, which implies basically the C1 up to Cn, they're all 0. So C1 is equal to C2 is equal to Cn is equal to 0, okay? And this tells you that the set is linearly independent, right? Thus, the set is linearly independent. Any question with this? Is it clear at all? All right, let's, so now we have n solutions to the differential equation, to ODE, the system of ODE, this one, okay? Forget about the initial value. We have n solutions, and we claim that these are the basis, okay, basis for this system. That means you can write any other solution in terms of this solutions. So let's write this as a theorem. Every solution of this system, x prime is equal to ax, can be written as a linear combination of x1, xn. Okay, there's one question, how we get this here. Well, this is equivalent to that one, okay? If you expand this, maybe let me write this here. It's basically C1. It's basically C1 times 1, 0, 0 plus C2 times 0, 1, 0, okay? And you go like this, Cn times 0, 0, 1 is equal to 0, 0. And it is the same thing, okay? So instead of writing this, you can write that one. They are the same. Can you see this? Yeah. All right.
Ama hocam identity'de olduğu için sadece C1, C2 kaldı değil mi? O yüzden de sıfır eşitledik.
Evet. Identity ile bir, değil mi? Şeyi çarparsanız o şey değişiyor.
Kendisi oluyor.
Aynen.
Teşekkürler.
Rica ederim. Any other question, comment? Well, okay, then let's continue. So now here we were talking about this. We have the system. It's not IVP, it's a linear ODE, system of ODE. Initial values are not given. But with some initial values, we have the solution x1, x2, xn. And these solutions the solutions make a basis for the system, okay? Maybe let's write here, that is this is a basis for the solutions of, let's call it star here, star, okay? It makes a basis for this solution set. Well, let's maybe prove this quickly. Well, don't worry, we will do many examples later, but we have to do this theoretical part first and do some examples later, okay? The proof is, it's just one line. So suppose that, so we will take an arbitrary solution and we will write that solution in terms of these solutions. So suppose that x is a vector function and is a solution to star. So let's say we have one solution and it has some initial value, right? Say x at t0, at some point t0 it is equal to a vector, a constant vector, k1, k2, kn, okay? It's equal to that vector. Then we had this x1 up to xn. Let's look at this and consider this function, this vector function, x1, k1 x1 plus k2 x2, oops, sorry. Kn xn, we know that this is a solution, of course, right? Because of the principle of superposition, any linear combination is a solution of the system as well. Let's maybe, okay, maybe let's say this is a solution to start by principle of superposition. And what is the value at t0? At t is equal to t0, let's see what we get. K1 x1 t0 plus k2 x2 t0 plus kn xn t0. Well, this is k1. x1 t0 is x1 is the solution with the initial value 1, 0, 0. And x2, for x2 it is k2 0, 1, 0, 0. And you go like this. Kn 0, 0, 1. So what you get is basically, it's nothing but K1, Kn. So you see, the initial condition here is same as the initial value here is same as the initial value here. But there is only one solution to the IVP. That means this function must be same as this function here, the whole thing here, right? Because they have the same initial values, okay? But there's only one solution. So by uniqueness theorem, the arbitrary function x, the arbitrary vector function x is equal to this linear combination, okay? So by uniqueness of the solution to IVP, which IVP? X bar is equal to AX and X T0 is equal to K1, Kn X is equal to K1, X1, this combination here, okay?
Hocam biz bu k ve x'lerin çarpımını nasıl yazdık? Neden yazdık? Tam olarak anlayamadım.
Bir dakika. Kn, Xn. Bir daha sorar mısın?
Neden k ve x'leri çarptık?
Neden k ve x'leri çarptık? Çünkü herhangi bir solution aldık. Burada herhangi bir çözüm aldık. We take an arbitrary solution here and our purpose is to write this. Yani bunu diğer spesifik çözümler var. Onların kombinasyonu olarak yazmak istiyoruz. O kombinasyonda şu aldığımız vektörün T0'daki değerini hesapladık. Bu sayılar o kombinasyonu belirledi. X'i rastgele bir çözümü daha önce bildiğimiz çözümlerin kombinasyonu olarak yazabildiğimizi göstermek istiyorduk. O katsayılarda T0'daki değerinden geldi. Onu gösterdik.
Teşekkürler.
Hı-hı.
Hocam o zaman A matriksinin size'ı kadar solution set'in base'i mi oluyor?
Evet, güzel. Güzel bir şey. Bundan bahsedecektik zaten.
Tamam.
We will talk about this.
Tamam o zaman hocam. Sorun yok.
Yeah, so there are going to be n independent vectors in the basis for a system of n equations and n unknowns. Right. So the system here has the initial value, okay, and this initial value determines the coefficients of here. That's right. That's right. So basically, if you know this spatial solutions corresponding to spatial initial value, you can write any other solution with this constant coefficients. Okay. All right. Good. Let me give an example before the break. I mean, it's not a concrete example, but it will explain a little bit what we did here. So suppose that we have a system like this. X prime is equal to A 2 by 2 times X, okay, times X. Say this has solutions. X1, X2. These are spatial solutions corresponding to initial values. One, 0, and 0, 1, respectively. Okay. Then take any other initial value, then consider IVP. By this, for instance, X prime is equal to AX, okay, and X prime, X of t, sorry, at some t0. This is, let's say it is 2 and 3, okay. Then the unique solution to this IVP is basically 2 times x1, sorry, 2 times x1 plus 3 times x2. Okay. So if you know the spatial solutions with elementary initial conditions, then you can write solutions to IVP with any initial condition, okay, by a combination of these two. Is it clear what we are doing here? Well, we will do some concrete examples, but let's do this part first. Maybe let's give a break here for 10 minutes. So let's meet at 11:40.
Hocam araya gitmeden bir soru sorsam.
Tabii.
X1, X2 corresponding initial values diyoruz ya. Burada tam olarak demek istediğimiz şey ne?
Yani
neyin initial value'sine correspond ediyor?
Initial value problem şöyle yazdık. AX x t0 is equal to 1, 0. This is an initial value problem, and the solution is solution vector x1. x1 is a vector like this, x1, 1, t, x1, 2t, okay? It's a solution of this initial value problem. The other one is the solution when we replace the initial value by this, okay? Yani diğeri de
Anladım.
initial value 0, 1 aldığımız zamanki.
Farklı iki initial value problem'ın çözümleri, bu da onun
Evet.
kombinasyonu oluyor.
Evet. Evet.
Yenisi.
Evet.
Teşekkürler.
Hı hı. Var mı başka soru? All right. Break now. All right, let's continue. Before we continue, do you have any question? Kübra, you say initial vector always consists of 0, 1. Well, that's not really true. Initial vector can be any vector. Okay. Initial value can be any value you take. The solutions here, maybe you're talking about the solutions here. The solutions, the basis for the solution is not a unique solution. There might be different bases. We will see this in some examples. Okay, so we cannot say that the initial the basis functions are in this form or in that form. It's not true. They can be in different forms. Okay. Okay, let's maybe let's write this definition of basis in general. This is the definition. Well, we say a linearly independent set B. B is the name of the set. Okay, set of solutions. Well, there is one question. What is x1 and x2? X1 and x2 are also they are vector functions. You can also think of matrix, right? So x1 is like this, for instance. I'm just making up. This is like sine t, cosine t, for instance. Okay, and it's a 2 by 1 matrix. You can think of 2 by 1 matrix. Okay, but it's a vector anyway. Any vector is a matrix, right? With one column only. Well, right. Well, here this is the spatial basis, elementary basis we call it, but in general, we may have different bases. All right, so basis is not a unique set of n functions, n vectors, but you're right. In this case, we have the spatial basis. For spatial basis, we have the initial values, this elementary vectors like 1, 0, 0, 0, 1, 0, and so on, but the basis need not to be like this in general. Okay, you're right. Okay, let's talk about the basis now. A linearly independent set B of solutions of x prime at x such that any other solution can be expressed as a linear combination of B is called a basis. Is called a basis. Of basis for the space of solutions. Okay. So if you have, let's say you have an n by n vectors, matrix, and the system has n independent solutions, and if you have n independent solution as a vector functions, then this set is called a basis. Let me write this as facts. So is this clear what a basis is? You have some number of vector functions, and you write any other solution in terms of this solutions. Well, usually the solutions to ODE, the system, we have infinitely many solutions, but the basis has finite number of solutions, okay? And you write any solution in terms of this basis elements. Let me open new page. So there are some facts. Remember, X1. So this is the spatial set of solutions with some spatial initial values, right? With 1, 0, 0, 0, 1, 0. This set is a basis. We just show that, right? Any other solution can be written in terms of these ones. So this is a basis for the solutions of x prime is equal to ax. We proved this earlier, right? In the previous theorem, because basis means you can write any other solution in terms of this one, so it's a basis.
Sorry, can I ask a question?
Sure.
Can we assume that this set is like sets of solution with a coefficient of 1?
What do you mean?
Like this basis includes all set of solution, but with the coefficient of 1.
With the coefficient of 1 means
Like
what?
we sometimes write k like something near the x1, x2. We write something like some coefficient.
Well, any other solution, let me explain maybe. Any other solution, take a solution like this, okay? It's a solution of this system. Then that means you can write this as a combination of k1, x1 plus k and xn. Here, ki's are some real numbers, okay? So this is what
Yeah, so I mean, can we assume that like k1 and so other goes like k2 is all equal to 1 in the basis?
That gives one particular solution. It's also a solution, but it's only one solution, okay? It gives you one solution. In that case, you fix a solution.
Yeah, so this fixed solution is called the basis.
No. What I'm saying is the basis is the set of this solution, but if you take, for instance, this vector, the spatial vector, let's say x tilde, which is x1 plus xn, right? You are saying this, right? So k1 up to kn is equal to 1. It's a solution, is a solution to this one, okay? This equation. But there are also other solutions. So in order to get other solutions, we need to change this coefficients, okay?
Okay, yes, I got it. Thank you.
And this is actually the solution of this system with the initial value. What is the initial value here? The initial value will be 1, 1, 1, 1, okay? They will be all 1. xt0 is equal to this, right? Get it?
Yes.
Yeah, good.
Hocam bir soru da ben sorabilir miyim?
Sor bakayım.
X1'den X'e kadar şimdi bunlar basis ya. Mesela altta bir tane çözüm yazalım. X vektörü atıyorum 2x1 artı 3x2 olsun.
Hı hı.
Bu da base'in bir parçası olabilir mi? Yani basis minimum number of vektör mü içermesi lazım yoksa
Evet,
redundant?
Onu şimdi söyleyeceğiz. In a basis, we have same number of elements. Every basis has same number of elements.
Yani mesela bunlardan üretebildiğimiz başka bir solution'ı base'e koyarsak artık o base olmaktan çıkıyor değil mi?
Evet, evet, evet.
Tamam.
Yani her basis'de aynı sayıda vektör oluyor. Bunu
Tamam.
soruyorsun değil mi? Okay.
Evet, evet.
That was I was gonna talk about it now. So let's write it here. Any other basis has the same number of elements. Okay. So if you take any other basis, there might be different bases, okay, for the same system, but number of vectors will be the same. If you have 3 vectors in the basis, in a different basis, you will have again 3 vectors, okay, 3 vector functions. And we're talking about here the system with n equations and n unknowns. So this is an n by n matrix, okay? Then this basis, any basis has n solutions, n elements, namely n vectors, okay? N many vectors. And this says if you have n linearly independent solutions, it's a basis, okay? This is important because in order to check whether we have a basis or not, it's enough to check we have enough linearly independent vector functions. Any linearly independent set of vector functions containing n solutions is a basis. Okay, so let's say you have solutions. Let's say you have 3 by 3 system, and you have 3 vector functions which are linearly independent, and they are the solutions of the system. So it's a basis. So this is what it says. Okay. Any question so far? All right. The question is, how do you check the linear independence of the solutions? This is what we did earlier. It's quite similar to what we did earlier. Let's talk about this. The question is, how to check linear independence of the solutions of x prime t is equal to ax. Right, with Wronskian, right? So you will check the Wronskian, and this will tell you whether you have a linearly independent set of vectors. So let's talk about this now. So let's say we have some solutions. So let x, I will put the index here now. So that means these are arbitrary solutions, x sub 1, x sub 2, vector functions, not a spatial one, any arbitrary solution of the system. B, solutions to this ODE, the system, solutions to this system, okay? We have n solutions, and here A is an n by n matrix. Let's see whether we have a linearly independent solution. So what we do is to check linear independence, to check linear independence. We check this, C times x1 plus C1 times x1 plus Cn times xn. Let's say this is equal to 0, and we will check whether the coefficients are all 0. But this tells you what? This tells you basically you can write the system, okay, the system in a better way. Write a matrix like this. We don't need this notation. So this is like x1. x1 is the first column, okay? So you take this vector, remember this is a vector, and you put this in the first column. The second column is x2, okay? And you go like this, xn. This is now an n by n matrix. So these are columns, okay? Column vector, column 1, column 2, column 3. It's an n by n matrix. And you multiply this with C1, Cn. It's a matrix multiplication, and you get this is equal to 0. This is basically the same. Can you see this?
Hocam zero matriksi elde ediyoruz değil mi?
Zero matrix, yeah, right. Here, zero matrix, okay? Zero vector or matrix, right? Okay, there's one question here. We use subscript instead of superscript. The reason is we use superscript here for the spatial solutions. So these are the spatial solutions corresponding to 1, 0, 0, 0, 1, 0, okay? And the subscript here, this is an arbitrary solution, okay? We don't know the initial conditions here. All right? Just to make this difference. Other than that, we can use subscript, superscript. So these are just notations, okay? Maybe let's say arbitrary solutions. The arbitrary. Yani herhangi bir çözüm. Özel işte 1,0,0'a karşılık gelen çözüm değil bu. Initial value'su. Tamam. All right, so we can write the system in the matrix form like that. Then this tells you what? This tells you basically if the Wronskian, now what is the Wronskian? Wronskian is a determinant. So if the determinant of this matrix, x1, xn remember these are functions. Maybe let's write with the variable as well. x1t, it's a function. xnt, it's a function. Here as well, the same, x1t, xn. Well, I didn't write it, but they are all functions of t here. This is a function of t, this is a function of t, it's a function of t. It's a vector function, okay? But I didn't put this here to make it simplify, so let's remove it anyway. Okay, so if this determinant is not equal to 0 at some point t is equal to t naught, then what? Then the matrix has an inverse. Then this vector c1 up to c1, cn must be 0, right? If the left-hand side, the matrix has an inverse, then you cancel out this matrix with the inverse, and you end up with c1 is equal to c2 is equal to cn is equal to 0, right? We did this earlier, right? We talked about this similar thing. When we have determinant non-zero, then we have an invertible matrix, and the coefficient must be 0. And this implies the set of solutions x1 xn is linearly independent. Okay, any question?
Yes, can I ask a question?
Sure.
Don't we need to take n-1 times the derivative?
That's a good question. It was for set of functions. Now we have set of vectors. Remember,
okay.
For this case of set of functions, in order to make a system, we take the derivatives. Here we already have vectors, and that makes the system, okay?
Thank you.
We don't need derivative. And now this is also called the Wronskian, okay? So Wronskian can be defined in terms of vector functions or as earlier with derivatives. They are both called Wronskian. So this is, maybe let's note this here. This, not this one, but the determinant here. This determinant here is the Wronskian of x1 xn. Okay, it's also called the Wronskian of these vectors. So basically, if the Wronskian is non-zero at some point, then you have a linearly independent set. Well, there is one nice thing, maybe let's write this as a fact. Again, it follows from existence uniqueness theorem. The Wronskian, so maybe let's say first. Right, so these are the solutions, x1, t, okay? X and t, you compute the Wronskian, basically you make a matrix and you take the determinant, and this is equal to, let's say, if this is equal to 0 at some point t is equal to 0, t0 is equal to at some point t is equal to t0, at some point t0, then the Wronskian is identically 0 at any other point. Okay, then the Wronskian x1 t xn t is 0 for any t. Okay, it's not a trivial fact. Again, it follows from existence uniqueness theorem, but let me not go to this. So keep in mind that the Wronskian, the solution vectors of Wronskian of the solutions is 0. If it is 0 at some point, it is 0 everywhere. So basically it says the Wronskian is either identically 0 or it is never 0. Okay. So you don't need to search for a specific value where the Wronskian is non-zero. If it is 0 at some point, it is 0 everywhere. Okay. So this is what it says. No, what I'm saying, well, in this case, yes. Okay, the question is, in this case, we don't have any solution. That's true. In the case of Wronskian is 0, well, it says something about the linear independence, right? In that case, if the Wronskian is equal to 0, we have infinitely many solutions, okay? Infinitely many solutions for the constant C1 up to Cn, and in that case, the system is linearly dependent, okay? Linearly dependent. Maybe let's write this as a summary. Summary. So let's say x1 xn be solutions of the system x prime is equal to ax, okay, this system. Then x1 this set is linearly independent. That means it's the basis. Because we have right number of linearly independent vectors and many linearly independent vectors. It's a basis. If and only if the Wronskian x1 xn is not equal to 0, okay? Even at one point or everywhere, because they are the same, right? Because of the fact above. So to show that we have a basis or not, we need to check the Wronskian. If the Wronskian is non-zero, even at some point, it's a basis. Otherwise, it is not a basis. Is that clear? Now we will do some examples. 7.5. We will solve some constant coefficient systems. So let us consider the ODE. X prime t is equal to ax t. Here, A is a constant coefficient matrix where A n by n is a constant coefficient matrix. Well, usually we solve the system with constant coefficients because the other one is quite difficult. And in this course, we will mainly deal with constant coefficient matrices. So this theorem here says how we find the solutions. Okay, so let A the above matrix be a matrix of real constants, real coefficients, and lambda be an eigenvalue of f with a corresponding eigenvector. V, okay? Then x t, which is e to the lambda t times v, is a solution to this system x prime is equal to ax. Okay. So, well, this is a nice theorem because it says how to find the solutions. We need an eigenvector, an eigenvalue, and this vector x in that case is a solution to this system. Let's maybe prove this in a line. So we need to check that this is a solution. Okay, this is a solution. Well, what is x prime? So x prime t is, v is a constant, so it's going to be lambda times e to the lambda t. This is the derivative of exponential times the vector. Okay, it's the constant. But that means basically you can write it like this: e to the well, eigenvalue means what? Eigenvalue means remember that means A times V is equal to lambda times V, right? Lambda is eigenvalue, V is the corresponding eigenvector. That means A times V is equal to lambda V. So we have here lambda times V, which is A times V, okay? So it is basically A times, you can write it like this. This is a scalar function. You can put it in inside, right? The multiplication with matrix. So it's going to be e to the lambda t times v, right? It is the same, a times this. But this is nothing but x, right? So we get that it is a times x, which tells you basically x is a solution, okay? X is a solution in this form, x is a solution of this system. Let's do one example.
Sorry, can I ask a question? Why is it x? I didn't get it.
Why is it what?
Why is it equal to x?
This one?
Mm-hmm. Yes.
It's the definition here. We define x like this.
Okay. It's the proof. Okay. Mm-hmm.
Good. X is in this form, okay? So that's why we have it, okay? All right, let's do one example and you will understand this better. So let's solve the system x1 prime, x1 is a vector, x1 prime is equal to 2 times x1 plus x2. x2 prime is equal to x1 plus 2x2. So here x1 is a function of t, x2 is another function of t, okay? And this is the system. We don't have any initial values here. Let's solve it. First, we write the corresponding system with the matrix. Well, let's say x, the vector is x1 and x2. Okay, then this becomes, the system becomes x prime is equal to, so we take the coefficient 2, 1, 1, 2, and we write the matrix corresponding to this system. 2, 1, 1, 2 times x1 and x2, which is x basically. Let's write it like this, x, right? So they are the same, right? And here is your matrix. This is your matrix A. Remember, the theorem says in order to find the solution, you need to find an eigenvalue, an eigenvector, and write the solution as this, okay? So let's find an eigenvalue. Eigenvalues. To find eigenvalue, remember, we look at the determinant. A minus lambda I. And solve this for lambda. Well, it becomes basically the determinant of A minus lambda I, 2 minus lambda 1, 1, 2 minus lambda, right? You subtract from the diagonal lambda and take the determinant, and it's basically 2 minus lambda square minus 1. Now let's see what we get. 4 plus lambda square minus 4 lambda minus 1, or you can write this lambda square minus 4 lambda plus 3. And the roots are, you can write this as lambda minus 3 times lambda minus 1. So there are two eigenvalues, 1 and 3. So lambda 1 is equal to 3. Lambda 2 is equal to, maybe let's write the smallest first. It doesn't really make any difference, but to be consistent, we write the smallest one first. 1 and 3. Let's find eigenvectors now. So eigenvector. Let's start with lambda 1, 1. So remember, we need to solve this, right? A minus lambda 1, which is 1, times I, x is equal to, or v is equal to 0. Let's say v is equal to 0. We will solve this, right? We will solve this to find v, and v will be the eigenvector. Well, what is this? This is equivalent. What is a minus I? You put basically here, in this matrix, you put lambda is equal to 1. And it becomes 2 minus 1. Which is 1, 1, 1, and 1, right? And it's equal to 0. So you solve this system. This is an easy system, right? Easy equation to solve it. You can use the elementary row operations, which is R2 minus R1 here, for instance, and it becomes 1, 1, 0, 0, 0, 0. That means here, maybe let's write v is like v1, v2. Okay, so v2 is free here because we don't have any condition for v2. They're all 0. That means v2 is free. Say it's k, okay, not equal to 0, and v1 plus v2 is equal to 0. This follows from the first line here, the first row here. v1 plus v2 is equal to 0. So this tells you basically v1 is equal to minus v2, which is minus k. And this implies the eigenvector v is k times 1 and minus 1. Okay. Is that clear? So we find one eigenvalue and corresponding eigenvector, then the solution. Vector is, remember it is e to the lambda 1 t times v, which is, you can take any eigenvector, choose only this one. When k is equal to 1, you can choose other ones as well. So it's going to be e to the t times v. V is -1, 1. Any multiple of this is a solution as well, so we can keep it like this. This is x. Let me give a name for this. Let's say this is x, x1. It's a solution, okay? Is a solution to the system, let's say. Well, we can do the same thing with the other eigenvalue. Now, lambda 2 is equal to 3. Then we solve this a minus 3i v is equal to 0, which implies now a minus 3i, so you put lambda is equal to 3 here, 2 minus 3 minus 1. Minus 1, minus 1, 1, 1. Okay, minus 1, minus 1, 1, 1. And you solve this system for v. Well, again, this gives you minus r1, and r1 plus r2 gives you the following: 1 minus 1, 0, 0, 0, 0. And again, here v2 is free. L free. Let's call it L, okay? And v1 minus v2 is equal to 0. So the solution is v is basically v1 is equal to v2, and there is L times 1, 1, right? v1 is equal to L, v2 is equal to L, so we get L times 1, 1. And the solution x2 is another solution, which is e to the 3t times 1, 1 is another solution. Well, this is basically, you can write it like this: e to the 3t, e to the 3t, okay? Is another solution to the system. Well, we have two solutions. It's a 2 by 2 matrix. Remember that the basis in this case has 2 elements, 2 vectors, and we have 2 solutions. If these are linearly independent, then they are the basis. Check the Wronskian for linear independence. Independence. We check the Wronskian of x1 and x2, okay? And it is what? Well, it's the determinant of x1. x1 is minus e to the t, minus e to the t, e to the t. x2 is e to the 3t, e to the 3t. And this determinant, you multiply this 2 and subtract this 2, e to the 2t e to the 40, sorry, minus e to the 40 minus e to the 40 minus 2 times e to the 4t, and this is never zero, right? Because exponential, it doesn't vanish, so it is not equal to 0. That means x1, x2 are linearly independent. Thus, it's a basis. Thus, this is a basis for the solution, okay? And the general solution to the system is x t is equal to c1 times x1 plus c2 times x2. Here c1 and c2 are real, or more precisely, this is c1 times, remember x1 is e minus e to the t, e to the t, plus c2 times e to the 3t, e to the 3t, okay? So this is the general solution, or if you want, you can write it like this. Minus c1 e to the t plus c2 e to the 3t, and c1 e to the t plus c2 e to the 3t, okay? And here c1, c2 are real numbers, okay? All right, we will stop here. Do you have any question? Hope everything is clear here.
Hocam sorunun başına bir gelebilir misiniz?
Okay. Well, for the exam, we will make an announcement later, so wait for it. It's not clear that what are going to be in the exam. So this is the question, okay. Var mı soru buradan?
Tamam hocam, yok.
Okay, let's stop here. See you on Friday. Bye.
Hocam
Hocam.
tekrar çözümün son halini alır mısınız?
Tamam.
Hocam bir de midterm 1'in saati belli mi? Yoksa duyuruyla mı gelecek?
Saatini sanırım syllabus'ta yazmıyor mu saati?
Syllabus'ta göremedim de sadece tarihi yazıyor. 15.04.
Bir dakika bakalım. Evet, saati henüz belli değil o zaman. Tamam. Onu da duyururuz. Yani bu hafta içinde duyururuz.
Tamamdır hocam, teşekkürler.
Initial value, okay, bu soru evet, initial value'yu verseydi C1, C2'yi ona göre bulurduk. Yani herhangi bir C1, C2 olmazdı. Initial value'ya göre C1, C2'yi sabitleri bulabilirdik, evet. Öyle bir örnek yapacağız. Peki, güzel.
Hocam bir şey sorabilir miyim çok kısa?
Şuraya.
Hani bu soruda Wronski'nin içine direkt biz yazdık ya, normalde türevlerini alarak gitmemiz gerekmiyor muydu bunu bulurken?
Bir daha nerede yazdık? Söyler misin? Ne yaptık?
Hani Wronski'ni bulurken x'i ve x'i 2 diye yazdık ya W'nin içine.
Evet.
Bunu yazarken normalde bunun kuralı şey değil miydi? Yazdıktan sonra fonksiyonları türevlerini alıyorduk.
Ama bunlar şey değil. Vektör durumunda onu yapmamıza gerek yok. Onu yapmıyoruz. O
Ha,
şey, fonksiyonların linearly independent olduğunu check etmek için türevlerini kullanıp bir matris elde ediyorduk. Burada vektör olarak veriliyor ya bunlar. Dolayısıyla bize 2 bir matris veriyor. Yani o yüzden türev almıyoruz.
Tamam hocam, teşekkür ederim.
Rica ederim. Peki. Görüşürüz arkadaşlar. Başka sorunuz yoksa.
Görüşmek üzere hocam. İyi günler.
İyi günler.